Before we start on any major algebraic work with trigonometric identities, let's warm up using our calculator. Here, we're given 3 trigonometric functions and asked to match them to their appropriate graphs, shown on the right. Let's take a second to set up our calculator in radian mode and put our window settings as shown on the screen. When inputting sine x over cosine x as our y1 function, it's important to close the bracket after the x of sine x. Otherwise, we'll get a very different graph, and that can be a little unsettling. Did you recognize that this was the graph of y equals tan x? That's because sine x over cosine x is equivalent to tan x. What do you notice about function number 2? Be careful, when I first looked at this, I thought it was maybe a reflection of graph number 3, but this is in fact something different. Cosine x over sine x is not a reflection of tan x, it is actually cotangent x. We'll revisit that in a minute. The graph for our third function might surprise you a little bit. It's a flat line. We call that a constant function, and here it's passing through a height of 1. But in a moment, when we look at our identity sheet, it'll probably make more sense. So, because sine squared theta plus cos squared theta is equal to 1 for all real values of theta, similarly, sine squared x plus cos squared x will always be equal to 1. That's why our graph didn't move up or down, but rather stayed at a constant height. We already discussed the tan theta and cotan theta. So, how do the graphs of both sides of an identity relate? Well, let's clarify this question a little bit. That's saying if we treated each side of an identity as a separate expression set equal to y, and then graphed each one, how would they relate? Of course, if it's an identity, that should mean that the two are equivalent for all values of x, and therefore their graphs should appear identically. Here we're asked to use our graphing calculator to sketch y equals cos x tan x. We're then asked if this curve is identical to the graph of y equals sine x. In blue, here is the graph of cos x tan x. Here in green is the graph of sine x. You can see that they appear identical. Once we use our trace function and input x equals pi over 2, in the first case, we get an undefined value, while the second case gives us a value of 1. What could explain this? Well, though the graphs appear identical, the cos x tan x could be written differently, and there we'll see how we've generated a division by 0. Let's walk through it. Because tan x is equivalent to sine x over cos x, we can rewrite this as cos x times sine x over cos x. And that division by cos x introduces the possibility of dividing by 0. So for what values is cos x equal to 0? Well, the first time is at pi over 2, and the next time is at 3 pi over 2, and then every pi after that. Notice, in the right graph, the y equals sine x, there is no division by an expression, so there's no possibility of dividing by 0, and therefore no undefined values. So, here we could say that cos x tan x is equivalent to sine x for all values of x that are not pi over 2 plus n times pi, where n is an integer number. We could see the same logic applied when comparing cotan x to sine x times cotan x. The moral of the story is, if you're dividing by a trigonometric expression or a trig ratio, be careful for values that generate zeros.